Welcome back into the MJ School of Mining and Geology YouTube channel. In today's session, we are dealing with the silicate classification. Okay, and so we're going to be looking at the group called the silicates, which is just a large group of minerals that are made up of silicon and oxygen. All right, and these silicates, they've got what you call the silicon tetrahedron structure, wherein we've got the silicon in the center, and this is surrounded by what we call the four oxygens, right? And then these silicates, we will be talking about olivines, pyroxenes, micas, and many others. But don't forget to like, share, comment, and hit the notification button below so that you get notified once we upload new content. So stay tuned. So silicate, like I said, these are the group of minerals which, they're abundant in the earth crust, and they're having what you call the silicon tetrahedron structure, wherein you've got silicon at the center surrounded by four oxygens. Okay, so basically that is that. It has got the same analogy as what you call a pyramid, or it has the same picture as what you call the pyramid. So basically we're going to be checking and looking at how this is what you call a building block. Okay, we're going to be checking how these atoms are arranged, or they bond together to form different silicates with different properties. Okay, and so basically that's what you're going to be looking at. Okay, and so the silicates are the most abundant in the earth crust. Why are they abundant in the earth crust? Because of the oxygen and silicon. Remember, silicon is the second best abundant element. So silicon and oxygen, they're abundant elements in the earth crust. Okay, and these silicates, they are considered to be rock forming minerals because of every igneous, sedimentary, and metamorphic rocks would have at least these silicates. Okay. And then they've got tetrahedron structure, or silicon tetrahedron structure, wherein we've got silicate at the center, not silicate, sorry, but the silicon at the center surrounded by four oxygens. Okay, that's why we say in this the tetrahedron structure, where one silicon atom is bonded to four oxygen atoms. And this structure is highly stable and can easily link with other elements like aluminum, magnesium, calcium, and iron to form a wide range of of minerals. And then, but though we're not going to talk much about it in this lesson, but also what you call silicon oxygen bond, which is very stable and strong. This would allow the formation of vast range of a range of minerals, which is why the silicates are considered to be the rock forming minerals. Okay. And then these silicon or these building blocks, they're going to be arranged or bonded together in a specific way, which would form different silicates, and these different silicates would have different physical and chemical properties. Okay, so basically you have to think of these as what we call the pieces of puzzles. All right, so for puzzles, you've got different pieces, and when you fit them together, okay, when you fit them together, they give you different shapes. So we're going to be looking at the pieces of the puzzles that when you fit them together, they would give you a certain picture. They would give you a certain silicate structure. That silicate structure would be having a certain physical and chemical properties. Okay, basically that's what we're going to be looking at today. And then we're going to be looking at these structures. Firstly, we're going to be looking at nesosilicates, sorosilicates, cycloinophyllosilicates, and the tectosilicates. But like I said, these things, you are basically looking at how the building blocks, they are fitting or they are bonding right? And then how they bond, they're gonna if they bond together, they're gonna give you a certain picture. Just like I said, like how different puzzles of or puzzle pieces can fit together in a unique way to form different pictures. Okay, but with nesosilicate, it's like we're having different pieces. It's like we're having different pieces which they are isolated. These pieces, we don't fit them together. We don't bond them together. They are isolated, these pieces. So it's like um, you're having these tiny building blocks, okay, which are what we refer to as the tetrahedra, and then which are made up of, silicon and the oxygen, okay, and then it's like they are like a pyramid. This structure is like a pyramid, all right. So basically, in nesosilicate, these building blocks or this tetrahedron, they don't connect. Okay, they don't connect directly to each other. Okay, but they are isolated. Okay, it's like individual puzzle pieces which they are just scattered around the table. Each one would be standing wherever, okay, on your table, so they don't fit together. So basically, that's what nesosilicate is all about. So we're going to be looking at the olivine as and the garnet as the nesosilicates, and then we've got sorosilicates and the sorosilicates. Then it's like now the pyramid, they are connected now. Okay, we have got two pyramids which they meet at the single point. Two pyramids which they meet at the single point. That's why we say the pairs of a tetrahedron, the pairs of the building block, or the pairs of what you call a pyramid. Okay. And then sorosilicate is basically the epidote, and we've got cyclo. We've got the cyclosilicates, okay, with the cyclosilicate. It's like now you're having the pairs of the tetrahedra, all right, and now you take those pairs of a tetrahedra or tetrahedron, and then you connect them in a ring shape fashion. So you take pairs, those pairs. Remember, in the sorosilicates, you're having two pairs of pyramids which are, are sharing one point. Okay. But now for cyclosilicates, you are taking these pairs which are sharing a single point, and then now you connect them in a certain style or in a ring-shaped pattern. Okay, so that now they start to form what we call a circular pattern. Okay. So basically that's that. And then we also have got what you call the inosilicates. The inosilicates, they're divided into a single inosilicates, which basically the pyroxenes, and then the double chains, which are basically what you call the amphiboles. Okay. So okay, inosilicates, they would form, long chains of tetrahedron, where each tetrahedron would share, oxygen atoms with its neighbors. But I'm going to show you how these things, they are, they are linked. All right, and then in the phyllosilicates is the sheet structures. All right, there's sheet structures, and then tectosilicates. The tectosilicates, the major or the common minerals are the quartz and the feldspars. Okay, so these pyramids, they are bonding in a three-dimensional framework. Okay. So basically, that's what we're talking about, that we are having this pyramid. This pyramid is what you call a building block. It's what you call a building block of what we call silicates. Okay, so this is what you call a building block. It's silicon tetrahedron with Si at the middle, or silicon in the middle, surrounded by 1, 2, 3, and another oxygen at the back, 4 oxygens. Then this is it. It will give you SiO4. Okay, silicon tetrahedra. Okay, so this is the building block. Now, like I said, these pyramids or these building blocks, they are like puzzle pieces that when you join them together, when you bond them together, they would give you a certain picture. They would give you a certain silicates with a certain properties. Okay, so but for isolated, those pieces, it's like you are just scattered. They are just scattered. They are you just have group of pieces which they are just scattered, and then that's why we say they are isolated. They do not bond. They are not linked. Okay, so that is that. For example, olivines and garnets, they've got that. And then now for iso, what we call the or silicates. In silicates or disilicates, you are having now the pyramids. These pyramids, they are going to be sharing, or they're going to be bonding, or they're going to meeting at one point. Okay, that's why we say a double tetrahedra, because we're having two pyramids which are sharing one point. But now for a ring, okay, for a ring or cyclic silicates, we are having now this double tetrahedra, and then this double tetrahedra, you join them in a ring shape, then they're going to form a circular, they're going to form a circular, they're going to form a circular pattern. So basically, that's what you do. And then for the what you call the inosilicates, like I said, inosilicates would be divided into two. We've got a single chain, and then we've got a double chain. Okay, so the inosilicates, okay, they are, they can either the way the tetrahedra they are arranged. Okay, we've got the one that is simple, and we've got the one that is complex. Okay, you can imagine this in this way, okay, as in you are connecting what you call the series of pyramids in a straight line. All right, here you are connecting a series of pyramids in a straight line. So that's how you can imagine a single chain silicate. You are connecting a series of pyramids in a single straight line. But now the most important point is each pyramid would share one side with the next. That is the most important part. Okay, although we are connecting a series of pyramids in a single straight line, the most important part is each pyramid would share one side with the next. If you can check, this is the first pyramid. This is the first pyramid. It shares one side with the next, and then even this one, it shares one side with the next, one side with the next. So all these things, they are sharing one side with the next. But now, because now they are connecting in a straight line fashion, they would form what you call a chain. You know, a chain, a chain, a chain. It would be something like that. Okay, it would be something like that. So if you the reason that's why we call them chains, because they are sharing one side. Okay. Now, depending on whether the chain is a single, it's a single row like that we find in pyroxene, okay, or it can be multiple rows. That now the multiple rows that will now connect in a ladder pattern. All right, you know the ladder, um, the ladder will be something like that. The ladder will be something like that. So it's like you're having that single here, you are having another single here. Remember the singles that each pyramid is sharing one side. You are having that pyramid in a straight line, which now they share one side, and then another one, and then they are connected in the middle. Okay, in a, what you call the ladder pattern kind of vibes. Okay, so the ladder pattern is found in the amphiboles. Okay, the ladder pattern is found in the amphiboles. So we can now see that this part is that single chain. Sorry, and also this part is that single chain. Then now they are having this part over here. Okay, they are sharing now these parts over here. Okay, they are sharing these parts. So now my screen is a bit messy. Okay, and then you can also have the, okay, you can also have the phyllosilicates, okay, or what you call the sheet structures, okay, sheet structures. So phyllosilicates are sheet structures, and for example, that's what we see in micas and what you call the clay minerals. So the micas and the clay minerals, they've got these sheet structures. Okay, so you know what you call a flip file, what we use to keep our paper safe. Okay, they are the phyllosilicates. They basically like the layers of tetrahedra. They are the like layers of tetrahedra. Okay, which are now these layers are stacked on top of each other like sheets of a paper. I can show you with this. If I can show you with this it's like phyllosilicates. It's like phyllosilicates. It's like phyllosilicates because of the tetrahedron are stacked, or the pyramids are stacked on top of each other like the sheets of the papers. So that's basically how you were to imagine this thing. Okay, you are having a thin flat sheets. Okay, you're having a thin flat sheets which are stacked together. Okay, where each sheet, okay, so you can think of this, that you are having a thin, for phyllosilicates, you are having a thin flat sheet. You are having a thin flat sheet which are stacked together, which are stacked together. All right, which are stacked together. But now, where each sheet, where each sheet, where each sheet is made up of connected pyramids. Connected pyramids, or the tetrahedron. Remember, I said that the pyramid is like the tetrahedron. Okay, okay, basically that's it. So you are having thin, flat sheets which are stacked together, where each sheet, all right, is made up of the connected pyramids. So these pyramids, you connect them, and then you form a straight line, then they form a sheet. And then you have another one on top of that, another one on top of that, another one on top of that. Now, if this structure is arranged in that fashion, it means you can easily peel these layers apart, just like how mica's flakes, they can be peeled off. Okay, why they can be peeled off? Because the layers are loosely held together, and they especially in micas, they're held by what you call a weak van der Waals force. Okay. And then now in the end, we are having the tetrahedra, or three-dimensional frameworks. Three-dimensional frameworks, or if you don't want to say three-dimensional frameworks, you can say the infinite tetrahedral network. That's what we basically see in quartz. And not only that, but also the zeolites and then feldspars. Okay, so basically what you see in tetrasilicates, okay, in tetrasilicates, you see what you call a three dimensional network. You see what you call three-dimensional network. A three-dimensional, you see a three-dimensional network. And then now this three-dimensional network will make a strong, stable structure. Okay, which is why quartz, they are, they are very, resistant, okay, especially to weathering. All right. Yeah, so because of this three-dimensional network, it makes the structure to become strong and, only not that, but also a stable one. So if you can look at this structure, is an infinite tetrahedron network, okay? So you can picture this as a web, okay? You can picture this as a web, or maybe a net, what you call a net, which is made up of, interconnected pyramids that would form a solid 3D shape. So these pyramids, they are in the form of what you call a web or a net. All right, they're in the form of a web. You know the web, the spider web. They're in the form of a spider web or a net, which this web, it is made up of what you call the interconnected tetrahedra, or a pyramid. And then this interconnected tetrahedra or pyramid would form a solid 3D shape. And then now these networks are incredibly strong, which is why quartz and feldspars are common and durable in rocks. All right, so they are common in many rocks because of their structure. Okay, because of this three-dimensional network, which is very strong and which is very stable because of the interconnection of these building blocks, which form a solid 3D shape. So that is that. Okay. So, like I said, in the nesosilicate, you are having the pieces, okay, or the group, or the silicon tetrahedron, or these building blocks, which are isolated, okay. And then they've got this general formula. And then example is olivine, the garnet, and the zircon. So you can now see that each silicon oxygen tetrahedron, or each pyramid, is isolated from each other. There is no connection. They are not linked to one another. There is no sharing of oxygen atoms between tetrahedra, and they are linked together by metal cations such as magnesium, iron, or the aluminium. So basically this is an olivine, and then the olivine has got this general formula. This is the general formula. It means you can have magnesium-rich olivine, or you can have iron-rich olivine, where in the magnesium-rich olivine, it will be termed a phosphorite. A phosphorite is the magnesium-rich olivine, and then the phyllite is the magnesium-rich olivine. Okay, so the general formula is this one, and then it has got these end members, phosphorite and the phyllite. Okay, so olivine is a group of silicate mineral composed primarily of magnesium and iron, which is why we find this in the mafic rocks, where in Fic it means iron, and the Ma it means magnesium, which is why mafic rocks, there are those rocks that contain high amount of magnesium and iron, but less quantities of the sodium, the aluminium, silicon, and of course, potassium. This would be found in high proportion in what you call the felsics, which where in sic it means SiO2, and then fel it means feldspars, which is why the felsic rocks, they are rich mostly in quartz and the feldspars. Okay, basically that is that. And then the structure consists of that, because this is the building block of silicates, where magnesium and iron occupy the sites between the tetrahedra. This is why these sites can be occupied by either magnesium or the iron. So basically, this is what we call an olivine, a greenish mineral. Okay, let me just clean the screen. Okay, let's move. And then now we are in the we talk about now the garnet. Okay, the garnet has got this general formula, and then we've got the A side and then the B side. Okay, we've got the A side and the B side. So depending on what metal or PS would be yeah, what metal will be filling this or what element, sorry, will be filling this A side or B side. Then you'll form different varieties like almandine, the pyrope, the andrandite, or the spartine. Okay, so garnet is a group of silicate minerals that share similar crystal structure but vary in their chemical composition. The structure would be the same but would vary in their chemical composition. The general formula indicates that garnet have two metal sides, the A side and the B side. Okay, okay. The A side can be occupied by calcium, the magnesium, iron, or the manganese. So because we are having A3. So this A, either the calcium, magnesium, iron, or manganese can occupy this A site. So it means you can have iron 3. If you have iron 3, you'll be talking about the almandite. If you have magnesium 3, you'll be having pyrope. If you have calcium 3, you'll be having what you call the andradite. But if you're having the manganese, you'd be having what you call the space and time. Okay, space and time. So, but now a B side can be having what you call the aluminum, or you can have a chromium, or you can have an iron. All right, so now if for example, now if you have iron and aluminum, now these, no, it's supposed to be two, sorry, not three, it's two. So if you're having aluminum and iron, that's where you form almandine and whatnot. So okay, now see that the garnet has two sides, which now is depending on what you are, what occupies which side, and then you can form different varieties of the pyrope, of the what do you call the garnet, like pyrope, spessartine, and other varieties. Okay, so that this is what you call the garnet. Okay, and we know the garnet is found mostly also in what you call the metamorphic rocks. Okay, and then we can also have the zircon, which many researchers they use. Okay, this is the general formula, the zircon. Okay, the zircon is a silicate mineral composed of zirconium and the silicon with oxygen, okay, completing the structure. The general formula, it's this one, like I've mentioned, sorry about that. Okay, and then the mineral has a tetragonal crystal structure, and zircon crystals are typically transparent to translucent. It means you can, when we say something is translucent, it means you can see inside, but you cannot see through. But if it's transparent, you can see through. Okay, that's how basically how the light is being transmitted. Okay. Often appearing in a wide range of colors, such as sometimes can be colorless, sometimes it can be yellow, sometimes it can be brown, sometimes it can be reddish like this. one. Okay. Zircon is important mineral for radiometric dating. Okay, so zircon is good for radiometric dating due to its ability to preserve the isotopic ratios of uranium and thorium, which are useful for determining the age of rocks and also the geologic events. And then now we've got the silicates, wherein we've got these two pyramids which are sharing or which are meeting at a single point. For example, the epidote and the vesuvianite. Okay. So these minerals, they occur in metamorphic rocks and may contain elements such as calcium and aluminum in addition to silicon and the oxygen. So basically this is an epidote. So this is an epidote. You can see the epidote, it has got this as the appearance looking like or it appear as the skin of a snake. Okay, that's how you can easily identify it. Okay, so the epidote, it has got this general formula. Okay. Okay, so epidote is a calcium aluminum silicate mineral with hydroxyl group, which is why you are having this hydroxyl group. Okay, you are having this hydroxyl group. Typical forms in metamorphic rocks such as schist and gneiss. Okay, schist and gneiss. Okay, this is the general formula, like I said, which indicate that epidote would obviously contain the calcium and it would also contain aluminium. And then silicon and oxygen, we are not surprised because it's from the building block, which is a silicon tetrahedra. Okay. But now, epidote, it has got this hydroxyl, it has got this hydroxyl group, and this hydroxyl group, it's meant to, balance the charges in the crystal structure, because the atom, it must always have the charges which are balanced. Okay. Epidote can have variations in its composition due to different substitutions. Sometimes iron, it can substitute the aluminum or the calcium. Okay. And then this is what you call the Vesuvianite, which is still a silicate. If you don't want to say Vesuvianite, you can just say idocrase, okay? Which now it's the calcium aluminum silicate, okay? Which also is found within the metamorphic rocks, and then it forms in contact metamorphism, okay? Often in marbles and skarns where high temperatures and pressures condition promotes its crystallization. So this is the Vesuvianite. And then we've got the silicates, wherein you are having the disilicates, and these disilicates or the disilicates, which now you connect them in the circular pattern, and then they will give you a ring kind of vibes. And then these rings, you've got, sometimes we've got the simple rings, and sometimes we've got the complex rings. And then you've got the beryl and its varieties, and then tourmaline and axinite. Okay. So cytosilicate form minerals that are often used as gemstones, such as the emerald, okay, and have significant industrial importance, okay, especially beryl. Beryl, it has got, there are varieties that can be used as the gemstones because they, they are very beautiful. All right, and one would need to wear these mineral either on their necks or rings, or with their rings or whatnot. Okay. Then that basically, that is the varieties of the beryl. You can see these the gemstones. They are lookable. They are eye-catching. And then with the emerald, which is this emerald. The green color is due to what we call the chromium or vanadium. And then we've got this heliodor. It's a bit yellowish. Okay, it's the same as you can confuse it with the what you call the citrine, but you know the citrine, it will have the conchoidal fracture, and then this one it won't. Okay, and then you basically, you know, identify this beryl because due to 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6. This structure, this hexagonal structure, basically that's how you're gonna be able to differentiate it from the rest. And then this pixtide, and then this is aquamarine. I always tell people that that's why it's aqua. Okay, it looks like water. Okay, or it looks like ocean. And then Maxis, the Morganite, and what you call the Trapic. Okay. So basically, these are the varieties of the beryl, and then the beryl having this general formula. This is the general formula of the beryl, and then the beryl, which is the aluminium silicate mineral, which often forms in granite and the pegmatite deposits. Okay. Sorry. Okay, so this is the tourmaline. Tourmaline, it's easy to be identified because it has got these different colors within it. You can see the bit reddish here, bit greenish here, somewhere it's clear, it's like here, you know, it has got this wide range of colors. And this range of colors result from different element substitution in its crystal structure. You are substituting different elements in this the crystal structure of this tourmaline, which is why it will have the variety of what we call the or range of colors. And then this will be the general formula, this long complicated one. Okay, so that's why a tourmaline, sorry, it's a complex borosilicate. Okay, that can obtain a wide range of elements such as sodium, calcium, whatnot, and whatnot, and whatnot. These things, that's why they make this tourmaline to become more impure and more complex. Okay. And then, like I said, we've got single chain inner silicates and the double chain silicates, which are just amphiboles. Can now see that the amphiboles, you are okay. Let's start with the straight line. Okay, you are starting with the straight line or the pyramids or the silicon tetrahedra, which are, you know, connected in a straight line vibe. And then now, if you are connecting these things in the form of a ladder pattern, they will give you a double chains, which are basically the amphiboles. Okay, which are basically the amphiboles. And then now, these minerals are common in igneous and metamorphic rocks and are often containing elements such as iron, magnesium, and the calcium. And now we are not surprised that from the Bowen's reaction series, the calcium one, then old people are boring. So olivines, and pyroxenes and amphiboles. Okay, so these are basically, they are mafics. So because they are mafics, you know, they must have magnesium, they must have the iron, and they must have the calcium. Okay, because these are high temperature elements. Okay, so yeah, that's why the amphiboles, they are double-sided, and this one pyroxenes are single-chained. Okay, so we've got two parallel chains. We've got two parallel chains. We've got the first chain. We've got the first chain. And then we've got another chain here, and they are parallel to one another, and they are linked here. They are linked here. Now this thing, it will form a ladder here. Like here, it will be kind of a ladder pattern. Okay? Yes. And that's why they are linked by additional oxygen atoms, forming a more complex structure. These are they will be linked by additional oxygen atoms. Okay? And then this one, Each tetrahedron shares two oxygen atoms with the adjacent tetrahedron, forming long single chain because you are having each tetrahedron which share oxygen atoms with adjacent. Okay, this would share with that one, that would share with that one, and so on and so on. Okay. Um, Then, yeah, basically that's that. The pyroxenes, you can have the enstatite, which is magnesium rich pyroxene. You can have a diapside, and then we can also have an augite. All right, and then basically this is what you call an augite, this is what you call an enstatite, and then this is what we call the diopside. Okay, so the pyroxene would be having this general formula, wherein the X and Y, where our X can be calcium, magnesium, or iron, and then it means X here you can be substituted by calcium, magnesium, or iron, and then Y it can either be iron, aluminum, or any other element. Okay, but like for example, like maybe magnesium, for example, in the diopside. Okay. So that's basically the pyroxenes, and this is a gyrite, a variety of a pyroxene. It's a variety of a pyroxene with the general formula of containing sodium and aluminium. So a gyrite is a more specialized form of pyroxene that is often found in metamorphosed rocks and is valued as a gemstone. So you can see you can make something beautiful out of this mineral. And then here we have got the igerin. Which is an iron-rich variety of pyroxene that typically form in alkaline igneous rocks. So this is igerin, which we expect to see in the alkaline igneous rocks, or the igneous rocks which are containing mostly calcium, potassium and sodium in higher concentration. Okay, then we've got phyllosilicates. Phyllosilicates, like I said, that these are basically a thin, flat sheets which are stacked together. Okay, and then where each sheet would be made up of the connected pyramids. Can now see that these are thin flat sheets which are stacked together. So these lines, they show staking. Okay, they show staking. Now that's why you can be able to peel things off, like what we say they are flakes, like what you see in the micas. Okay, you can peel these sheets off. Okay, basically that's that. And then, yeah, basically that's biotite. The biotite is the black one. So remember the micas, they have got this, what you call the cleavage in one direction. They've got the cleavage in one direction. All of them, they've got cleavage in one direction. So they've got the cleavage in one direction. They've got cleavage in one direction, all of them. They've got cleavage in one direction. So now that's basically how you can identify them because of the structure of their structure, having what you call the mica flakes. Okay, having what we call mica flakes, and then you can be able to peel these things off, and then you also have the capability to bend, and then if you release the pressure, they will go back to their original state. Okay, so now how can you differentiate the micas? The micas, because of in terms of all of them, they are having what you call the cleavage in one direction. You can differentiate them by color. So the black one, it will be the biotite. The light one, okay, and the light one or the colorless one would be a muscovite. If you can peel this thing off and then you have a one sheet vibe, and then you will see it's colorless, so it's clear, the kind of vibes. Okay, and then you can have a phlogopite, which is not that black, and it's not that lined, something in between. So that's how you can differentiate them based on the color. Okay, that's why we say muscovite is light colored, and then biotite is dark colored, and then phlogopite can have yellow or a brown mica. And then these are the general formulas. Okay, and then they've got their excellent cleavage. Okay, or cleavage in one direction. Okay, they've got cleavage in one, and then they've got these flexible sheets. Okay. So basically that's that about the micas. You should be able to physically identify these minerals, and not only physically, but also microscopically. Then we've got clay minerals. Clay minerals would include smectite, would include the elite, and then would also include the kaolinite. Okay, so these are the clay minerals, and kaolinite, it's a bit because sometimes people, they confuse it with the talc. But now remember, talc, it will be soft, okay, which is why talc is used for making what you call the baby powders. It's very soft, and because of the hardness of one, and then this one, it will be a bit rough as compared to talc. But now these things, for example, talc and kaolinite, which is why they're used mostly as the industrial minerals for making white paints, these papers, the ceramics and other things. Okay. So clay minerals are a group of phyllosilicates minerals that have small particle sizes and are often hydrous. Okay, which is why the general formula, it has got this H2O. Okay, they are often hydrous. They typically form from the weathering of other minerals and are found in soils and sedimentary rocks. So the clay minerals, they are found in sedimentary rocks. Okay, which is why when you are classifying the sandstones, for example, you are going to be checking the clay matrix. Okay, you're going to be checking the clay matrix, which is why they're found in soils and in sedimentary rocks. And then this is the formula for the kaolinite. This is elite, and this is the smectite. Okay, the smectite, it basically it will expand in water. So if you can immerse it in water, it will basically expand. That's how you see that this is a smectite. And then the kaolinite, it's white. Okay, that's how you'll be able to see that this is the kaolinite. It's a white clay. And then elite, why is it this a bit dark kind of vibe? It is because of the what you call the potassium. Okay, and then this one, you will know it by expanding it in water. Okay, then you also have what you call the talc. So I like this talc. Basically, talc, it will have the Mohs scale of what? Of 1. So how can you identify talc? By the softness. Okay, so you can just easily scratch it with your fingernail. All right, so basically these are the talcs that you basically can see. So usually people, they know this only this one, but now this one is still also talc. You'll see, if you can touch it, you will see it's very soft, giving the vibe that this is indeed talc. And the talc has got this, it has also has the, it's also hydrous. Okay, and is the magnesium silicate mineral, is the magnesium silicate mineral. Okay, that's why. Okay, composed of magnesium, silicon, oxygen, and hydroxyl groups. Talc is the softest mineral on the most hardness and has a greasy feel. It has got a greasy feel. It is used in a wide range of applications, including a lubricant, in cosmetics, and as a filler in various. It means they have to add its property in when you are mixing other things. Okay. So that's why these things, they are used as the industrial mineral. They are industrial minerals used for their industrial applications. And then tetrasilicates, this a what you call the three-dimensional network. Like I said, imagine this as a web or as a net. Imagine this as a net or as a web, which now it has got these pyramids that are arranged in a three-dimensional network, and then they will become strong and very stable. For example, quartz and the feldspars, and also not that, but also not limited to that, but also the zircon. Okay, and then for example, quartz. We've got the one which is clear. Why is it clear? Because it lacks impurities, does not have impurities, which is why it is clear. So a clear quartz, it does not have impurities. But immediately, remember, all the quartz, they can be identified by conchoidal fracture. They can be identified by a conchoidal fracture. And then now, that's basically how you know that, okay, now I'm dealing with the quartz. But now, how can you differentiate the varieties of quartz? The clear one, it means it does not have impurities. It's just clear. Okay, that's the normal one that we are usually exposed to. But now, you can have different varieties of quartz. The most common ones, they are rose quartz, the tiger's eye, chalcedony, which usually fills in the hollows, and the citron, the jasper, the amethyst, the agate. These are the most common ones, and the milky and the what you call the smoky quartz. Okay, that's why we say a clear quartz. Okay, it means it does not have any impurities. But if we can have an amethyst, this one, a violet colored quartz. Okay, this color is basically from the trace amount. You are having small amount of iron in the crystal structure, and then will give you this violet color. Then you can have also a rose quartz or a pink colored variety, where in this pink, it's resulting from the titanium 4 plus. Okay, titanium 4 plus. And then you can have what you call the smoky quartz, which is a dark colored variety. Okay, and then it has got well-formed crystals. You can see the well-formed crystals. Okay, and then this smoky quartz is due to the what you call that aluminum 3 plus. So smoky quartz, aluminum 3 plus, and then we've got citron, which is the yellow variety. This one is the yellow variety. Okay, and then you can have also a milk quartz. It will have the milk appearance. Okay, or it will have this waxy kind of vibe. But chalcedony, it will be the one which is waxy. Sorry. Then the milky quartz, it will have a milk appearance. Basically, that is that. So the quartz is usually clear because of lack of impurities, but immediately you have got trace amount of some aluminum, titanium, and other like the iron. Then you'd have different varieties of quartz. And then tiger's eye, it's the most simplest one, wherein you can be seen by what you call the tiger's eye. Basically, it's self-explanatory. It's having the tiger's eye. That's why it's tiger's eye. Okay. And then the feldspars, which is just also the tetrasilicates. So we know that the feldspars, okay, we've got the potassium rich here, we've got the sodium rich here, We have got the calcium rich here, and the feldspars, which has got the sodium and calcium end members. We call it a plagioclase feldspars, and then the one which having the end members between potassium and sodium is what we call the alkali feldspars. Okay, now how can you differentiate between an alkali feldspars and the the plagioclase feldspars? Okay, in the microscope or physically. Okay, but now the alkali feldspars, they have what we call the X solution lamellae. They've got X solution lamellae. Okay, this is due to that, this structure. This would be the temperature. Here the feldspar, it will be single. It will be one thing. When the temperature is high, the feldspars will be one thing. But immediate, because they are comfortable, they are stable in those conditions. But now, immediately when you change the temperature, when you lower the temperature, and then immediately when you hit this liquid immiscibility point, it means now you're gonna have the separation. Okay, you're gonna have the separation of these compositions, okay, which is why you're gonna have now these X solution lamellae that you see here. These are the X solution lamellae, and this X solution lamellae, it can also be seen in the blue variety of the alkali feldspars of the microcline, which is what you call the Amazonite, the blue variety. Okay, also it has got these Amazonite case it also has got this X solution lamellae. Okay. Now, that basically that's alkali feldspars. But now, obviously, in the microscope, they would have the alkali feldspars. They will have the albite twinning and other things. But now the plagioclases in the microscope, they would have what you call the polysynthetic twinning. That's basically how you can, easily identify them. All right. And then now, the thing like, for example, what you call the microcline and the orthoclase, they can easily be identified by this structure. Beside the X solution lamellae, they can easily be identified by this structure. Okay, can be easily identified by that structure. And then a sodium one, you like albite, and then you having, basically that, and then the calcium, it will be a bit milky. A calcium rich one will be a bit milky. This one is still it's what you call the labradorite, which is having a play of colors. Okay, but now this is not a perfect example of the labradorite, but it's having some striations. Labradorite, it has got this play of colors. Okay, so basically that is that. And then, so that's why alkali feldspars, they are calcium rich, like for example, orthoclase, which is a potassium feldspars, okay, and then the albite, which is the sodium feldspar, which is happening there at the left-hand corner. Okay, and then the plagioclases, we've got the albite and then anorthite. Can you now see that albite is a common factor? It's a common factor. It can be grouped as both the alkali and also as the plagioclase. Okay. And then the anorthite, for example, it will be, more whitish. Okay. Yeah. Um, then basically that is that about the tetrasilicates. And then the last one, it's what we call a zeolite, which is having what we call the water in its chemical structure. Okay. For example, we are having what you call the mondanite here. So it's the zeolite having sodium and the calcium. Okay, and then you also have got what you call the clip light. Hey, yeah, clinoptilolite. Yes. Hey, complicated. But yes, basically, you'll notice that all these zeolites, they are having water in their chemical structure. That is the most important part. And the general formula of the zeolite is this complicated. Sorry, is this complicated one. So it's complicated like the one of the tourmaline. All right. So zeolites are a group of hydrated aluminosilicates. They're having water in them. They're having water in them. And then the general formula reflects the presence of aluminum and silicon in a framework with the charge balance provided by alkaline sodium and sodium calcium and alkaline earth metals. Okay. And then the H2O represent the water content in the zeolites, which is a critical feature of their structure. Their distinctive feature, is the presence of the water. So the zeolites, they have got the water. Okay. So the formula also indicates that the aluminum and silicon can vary, giving rise to different zeolite species, which is why we've got different zeolite species. We've got so many zeolites, more than 15 of them. Okay, so I just gave you these two. Okay, so this brings us to the end of our session into what we call the silicates classification. So in today's session, we have learned that the silicates, they are the building blocks of the silicate minerals, which the silicate minerals are basically the rock forming minerals because they are abundant. They are abundant in the earth crust. And this silicon or the silicates, they are made up of the silicon tetrahedron, wherein we've got silicon at the metal surrounded by 4 oxygens. And then now this silicon tetrahedral or tetrahedra or tetrahedron is known as the building block of the silicate, and I like to refer to it as what you call a pyramid. It has the shape of the pyramid. So this pyramid is the building block. So how the pyramid, they connect, they give rise to different silicate minerals. And these silicate minerals, how they bond, how they link to, how these building blocks, they link to one another, they give us different silicate minerals which are having different physical and chemical properties. Thank you guys for joining us today. It has been the great session. I enjoyed this one because I always tell people that these ones, they are must know, minerals because they are rock forming minerals. It means you expect them in this in the igneous rocks, you expect them in the sedimentary and metamorphic rocks, and you see that most of these things, they are on the what you call the Bowen's reaction series, and there is no geologist who does not know what you call the Bowen's reaction series. So these minerals, they are really, really, really important for the what you call the rock identification. So thank you guys for joining us today. Please to show us support. Please like, share, comment, and hit the notification button below so that you get notified once we upload new content. And you know what I'm gonna say? I always like to say, until next time, cheers.